Now we are going to see a last method which belongs to the class of local averaging estimates as histograms and kernel methods, the nearest neighbor estimate. As for histograms and kernel methods, we want to estimate the density based on the points that are close to the query point x. More precisely, the k nearest neighbor estimate is defined in equation 55, where k is the number of k nearest neighbors considered in the algorithm, a parameter to be set in advance, n the number of observations, and vkx is the volume of the ball centered at x with a radius dkx. Here, dkx is the distance between x and its k nearest neighbor. Note that the k nearest neighbor of x is obtained by ordering the observations x1 until xn in an increasing order based on the distance to the query point x. The k nearest neighbor is quite logically the kth element of this ordered sequence. The volume of a ball of radius r in Rd can be obtained by multiplying the volume of the ball centered at 0 of radius 1 by the radius of the original ball r power d. Therefore, the nearest neighbor estimate in 55 only requires the distance between x and its k nearest neighbor to be computed. The resulting estimate is not a density, since its integral does not sum to 1. This is due to the renormalization factor vkx, which depends on the query point. The nearest neighbor estimate has also a lot of discontinuities because the nearest neighbor estimate does not vary continuously when you vary the query point. Besides, even for large regions with no observations, the estimated density is not zero, since you consider the ball containing the k nearest neighbors of x, which can be very large, making its volume also very large, and the corresponding estimate very small, but not equal to 0. Now, an exercise. Can you explain the intuition behind this estimate and try to find conditions on k and n such that this estimate is consistent? You can pause the video. Note that k over n, which appears in the estimate, can be written as in equation 57. Besides, under some specific assumptions to be defined, this term can be close to the probability on the right-hand side term in 57. This resembles the law of large numbers. If you fix x, dkx is small for k over n small enough. In this case, for any u in the ball centered at x of radius dkx, f of u is close to f of x if the density is continuous. The integral in 58 can be approximated in equation 59. Therefore, if we have k and n which tends to infinity, one can hope that 57 holds. A more rigorous justification would be needed here. The probability can be approximated by equation 59 if additionally k over n is small enough. Therefore, for k and n tending to infinity such that k over n tends to 0, one has equation 60, where the left-hand side is exactly the k nearest neighbor estimate. This gives intuition on why this estimate is consistent.